Morning. I welcome you all for the tutorial on steady-state molecular diffusion. Myself, Dr. E. Kavita, working as Assistant Professor in the Department of Chemical Engineering, School of Bioengineering, SRM Institute of Science and Technology. So in this video, I'm going to explain the problems in steady-state molecular diffusion, how to solve the problems in gas phase and also liquid phase, unique component diffusion and equimolar counter diffusion, and also how to solve pseudo steady state molecular diffusion problem. So we'll move on to the problems. So problem statement: ammonia diffuses through a stagnant layer of air 1 centimeter thick at 25 degrees Celsius and 1 atmosphere total pressure. The partial pressure of ammonia on the two sides of air layer are 0.9 atmosphere and 0.1 atmosphere respectively. Air is non-diffusing. Calculate the molar flux of ammonia. So DAB is equal to 0.214 centimeter square per second. When you read the problem statement, so two things you have to find out. One is whether it is gas phase diffusion problem or liquid phase diffusion problem. After identifying that, you need to find out whether it is unicomponent diffusion or equimolar counter diffusion. So let us check the problem statement. What is given? Ammonia diffuses through stagnant layer of air. So that means it is a gas phase diffusion problem. So since ammonia and air are given in the problem statement, it is the gas phase diffusion problem. Then whether it is unicomponent diffusion or equimolar counter diffusion. Again, let us go through the problem statement. Ammonia diffuses through a stagnant layer of air. So ammonia diffuses through stagnant layer of air means it is a non-diffusing component. And also there is one more statement given in this problem: air is non-diffusing. So only ammonia, that is diffusing component, and air is the non-diffusing component. So that means this problem falls under unicomponent diffusion in gas phase. Okay. After that, list out all the data given in the problem statement. Okay. So here what is given in the problem statement, that is represented in this image, in the diagram. Ammonia and air, these are the two components. Only ammonia is a diffusing component. It is given that 1 centimeter thick. So diffusion, we are going to consider between the distance 1 centimeter. So across this distance 1 centimeter, diffusion of ammonia takes place at 25 degrees Celsius temperature and 1 atmosphere pressure. So the temperature and pressure at which diffusion takes place, that is mentioned. Then the partial pressure of ammonia on the two sides of air layer. So that means across these two layers, what is the partial pressure of ammonia? That is what given as 0.9 atmosphere and 0.1 atmosphere. So in some problem, this partial pressure data will be given as a direct data. In some problems, it will be given in terms of either volume percentage or mole percentage of the components. So from the given data, either volume percent or mole percent, we have to find out its partial pressure. But here we are directly given with the partial pressure data. Okay. Then air is non-diffusing. That means it is the non-diffusing and ammonia is the diffusing component. So it is the unicomponent diffusion problem. So calculate the molar flux of ammonia. So we are going to calculate molar flux. And DAB, so diffusivity data, it's given. So let us see what are the data we have, right? So it's a unicomponent diffusion in the binary gas mixture. Total pressure is given. Temperature you take in terms of Kelvin. It is given in degrees Celsius, converted into Kelvin. Then Z, diffusion path distance, which is given as 1 centimeter. So that means 1 into 10 power minus 2 meter. Then partial pressure of ammonia across the two, at the two layers. So PA1 0.9 atmosphere, PA2 0.1 atmosphere. Then diffusivity data given in centimeter square per second, you have to take in terms of meter square per second. Okay. Then solution part. So first write the formula and check whether we have all the data for calculating molar flux. So you are given with the molar flux formula. So Na refers molar flux of component A, that is equal to Pt by Rt dAb by Z ln of Pt minus Pa2 by Pt minus Pa1. So this Pt refers total pressure. R is gas law constant. T is absolute temperature. DAB is diffusivity. Z is the distance through which diffusion takes place. PA2 is partial pressure of component A at layer 2 and PA1 is partial pressure of component A at layer 1. Let's check whether we have all the data. So PT, total pressure, that is given, and also it is given in atmosphere. So directly you can substitute the data. If it is not given in atmosphere, please try to convert it into atmosphere, then substitute. Then R, that value will not be given in the problem. You are supposed to remember the value of R. There are various values of R with the different units. And here I am going to use the value of R as 0.08206 meter cube atmosphere kilo per kilomole Kelvin. Then T, absolute temperature, that is in terms of Kelvin. Diffusivity in terms of meter square per second, that is also given data. Z, diffusion path distance, going to substitute in terms of meter, that is also given data. Then PA1, PA2, both are partial pressure data with respect to ammonia. All the data are given. Just you're going to substitute in the formula and find out molar flux. So R, as I mentioned, 0.08206 meter cube atmosphere per kilomole Kelvin. So based on this R value, the pressure which you are going to substitute, that must be in atmosphere, temperature in Kelvin. So by substituting all these values, you will be getting the value of molar flux. So I hope you have understood. Next, we'll move on to next problem. Problem statement. Helium and air are contained in a conduit 7 mm in diameter and 0.08 meter long at 45 degrees Celsius and atmospheric pressure. The partial pressure of helium at one end of the tube is 0.075 atmosphere and 0.03 atmosphere at the other. Calculate the molar flux of helium for the steady state equimolar counter diffusion. DAB is 6.2 into 10 power minus 5 meter square per second. So first, as I mentioned, you have to find out whether it is a gas phase diffusion or liquid phase diffusion. Just go through this problem statement. Helium and air. So both are gaseous components. So obviously it is a gas phase diffusion. Next, you have to find out whether it is a unicomponent diffusion or equimolar counter diffusion. In the problem statement itself, it is clearly mentioned that steady state equimolar counter diffusion. So this is the equimolar counter diffusion in gas phase, and it is there are two components, so it is a binary mixture of gas. So it is mentioned that these components are contained in a conduit 7 mm in diameter and 0.08 meter long. So there are two conduits in which you have helium and air. So these two conduits are separated at a distance of 0.08 meter and the diameter of the tube is 7 mm. So this distance between these two conduits, that is the diffusion path distance, which is 0.08 meter. And the diffusion takes place at 45 degrees Celsius temperature and atmospheric pressure. That means 1 atmosphere pressure. Again, in this problem also you are given with the partial pressure data. So directly you are given with the required data. So partial pressure at one point and partial pressure of helium at the other point. So both the data are given and also given in atmosphere. Then we are supposed to calculate molar flux of helium. Diffusivity data is given. So let us list out the data first. Write down the data. So write the condition of diffusion, equimolar counter diffusion involving binary gas mixture. Total pressure 1 atmosphere, temperature in Kelvin, distance 0.08 meter, partial pressure of helium at one end of the tube, which is PA1, other end of the tube, which is Pa2, then diffusivity data. So we have listed all the data. Next, let us move on to the solution. First, write the formula for equimolar counter diffusion in gas phase, and let us check whether all the data are available or not. So this is the formula for calculating molar flux. So DAB by Z RT PA1 minus PA2. So where Na is molar flux of component A, DAB is diffusivity, R is universal gas law constant, T is absolute temperature, Z is the diffusion distance, PA1 and PA2 are partial pressure of component A at plane 1 and plane 2. So let us check whether these data are given in the problem statement. So DAB diffusivity data, that is given, T temperature is given, Z that is also given, R value as I mentioned in the previous problem, the value will not be given. You are supposed to remember R value. Depending on the R value, the other factors unit you can decide. So I am going to select R value as 0.08206 meter cube atmosphere per kilomole Kelvin. Based on that, I can take temperature in Kelvin, pressure in atmosphere. By substituting all these data in the formula, you will be getting the molar flux value. I hope you have understood this. Let us move on to the next problem. An ethanol water solution in the form of stagnant film 2 mm thick at 293 Kelvin is in contact at one surface with an organic solvent in which ethanol is soluble and water is insoluble. At point 1, the concentration of ethanol is 16.8 weight% and the solution density is 973 kg per meter cube. At point 2, the concentration of ethanol is 6.8 weight% and density is 988 kg per meter cube. Diffusivity of ethanol is 0.7 into 10 power minus 9 meter square per second. Calculate the steady state molar flux of ethanol. So what is the first step? You have to find out whether it is a gas phase diffusion or liquid phase diffusion. So it is given that ethanol and water solution. So obviously this is liquid phase problem. Next point, you have to check whether it is a unicomponent diffusion or equimolar counter diffusion. So what is given in problem statement? Ethanol water solution in the form of stagnant film 2 mm thick. So here it is in contact with the organic solvent. So just visualize that you have the solution which is containing ethanol and water that is made into contact with some organic solvent. So in that organic solvent only ethanol is soluble. So that means so ethanol will diffuse through water and it will get dissolved in organic solvent. Okay. And water is also given. Water is insoluble. That means water is not going to diffuse. Only ethanol present in the solution will diffuse through the solution and it will get dissolved in organic solvent. So here ethanol component A is diffusing component and component B water, that is non-diffusing component. So this problem falls under unique component diffusion in liquid phase. Okay. Then at a point 1, concentration of ethanol is 16.8 weight% and the concentration corresponding to the, density corresponding to that. Similarly, at point 2, concentration in terms of weight percentage and corresponding density are given. So these data will help us to calculate mole fraction data. Then diffusivity of ethanol, that is also given. Okay. So we'll write down all the data given in the problem statement. Okay. So in the liquid film, ethanol, water you have. So ethanol is only diffusing and the distance through which diffusion takes place is given as 2m. Okay. And temperature is 293 Kelvin. So it is a unicomponent diffusion in binary liquid phase system. Temperature as such given in Kelvin, you can note down. Then Z in mm it is given, take down in terms of meter. Then weight percentage of ethanol at 0.1 and 0.2 are given, corresponding to the density data are given. And diffusivity. So you need to calculate steady state molar flux. So let us move on to the solution. First, write down the formula and check whether all the data are available or what are the data we are supposed to calculate in order to get molar flux. So formula Na is equal to dAB by Z, rho by M average, ln of 1 minus XA2 by 1 minus XA1. So in this, Na refers molar flux of component A, dAB is its diffusivity, Z is the diffusion distance, rho by M average is the ratio between density to molar mass of the solution. Then XA1 and XA2 are mole fraction of component A at film 1 and at film 2. So next we'll see whether we have all the data to substitute in the formula. So DAB diffusivity, it is given. Z, that is also given. Rho density of solution at two different concentration, that is given. So M average molecular weight not given. XA1, XA2 mole fraction of ethanol at 0.1, 0.2. These data are also not given. So we need to first calculate these unknown data. Then only we can move on to the calculation of molar flux. Let us see one by one how to find out the required data. So first I'll explain about how to find out XA1, XA2. I mean mole fraction of A component at film 1 and film 2. So mole fraction. So what is mole fraction? Mole, number of moles of the individual component divided by total moles. So can we write moles as mass of the component divided by its molecular weight? Yeah. So I have written in XA1 formula as moles of ethanol divided by total moles. So total moles is moles of ethanol plus moles of water. So moles I have written in the form of mass divided by molecular weight. So mass of ethanol by molecular weight of ethanol, whole thing divided by mass of ethanol by molecular weight of ethanol plus mass of water by molecular weight of water. In your problem statement, we are given with the conditions of weight percentage of the component at the two film. So weight percentage of ethanol at film 1 it is given, weight percentage at film 2 is given. Let us now see at what is the concentration with respect to film 1. So you are given with the concentration at film 1, right? So if I take the basis as 100 kg of solution, whatever the weight percentage given, that can be taken as the weight of the component. And so if I know weight of component A, 100 minus weight of component A will give me weight of component B. So I'm taking basis as 100 kg of solution. So from weight percentage, I'm getting weight of component A. Then by subtracting that value from 100, I'm getting the weight of component B. So by using weight of component A, I mean ethanol, weight of component B, water, and substituting in this formula, I'll be getting XA1. For molecular weight of ethanol, you can make use of the molecular formula, and from there you can find out its molecular weight. So molecular formula of ethanol C2H5OH. So using that, you calculate the molecular mass and substitute in the formula. The next, mole fraction of ethanol at 0.2. Again, here also same formula, moles of ethanol divided by total moles. Then for moles, that is written in the form of mass per molecular mass. The weight percentage data is given. So we'll take the basis as 100 kg weight of solution at film 2, and based on that, weight percentage of ethanol can be taken as weight of ethanol. So 100 minus weight of ethanol will give you weight of water. So once you have weight of ethanol and water, we can substitute in this formula for finding XA2. So I have XA1, XA2. The next to my calculation is average molecular weight. There are various ways by which you can find out average molecular weight. What I have given is one way of calculating average molecular weight. So that is total mass by total number of moles. So total mass of solution based on the basis which we have chosen 100 kg. Then the moles calculation, what we have done in mole fraction calculation, same way you can do it in denominator part. and you will be getting M1 average molecular weight of solution at 0.1. Then similarly, average molecular weight of solution at 0.2. So total mass of solution divided by total moles. So total mass of solution based on basis, it is 100 kg. Substitute that, and denominator factor, that is more or less similar to what we have done in XA2 calculation. So you can substitute here. Then rho by M average. So by taking the ratio average of density and molecular weight at film 1 and 2, you will be getting rho by M average. The next, by substituting all the data in flux formula, you will be getting molar flux. I hope you have understood. We'll move on to the next problem. Ammonia is diffusing through a stagnant mixture consisting of 1/3 nitrogen and 2/3 hydrogen by volume. The total pressure is 206.8 kilonewton per meter square and the temperature is 55 degrees Celsius. The concentration change across the film is from 10% to 5% of ammonia by volume. Diffusivity data at 1 atmosphere and 25 degrees Celsius is given. That is given as 1.82 into 10 power minus 5 meter square per second. Calculate the rate of diffusion of ammonia through a film of gas 0.5 mm thick. So here it is given that ammonia is diffusing through stagnant mixture of nitrogen and hydrogen. So since three components are involved, this is a multi-component system and the components are ammonia, nitrogen, hydrogen. So it is a gas-phase system. So it is a multi-component gas mixture. Next, whether it is a unique component diffusion or not, we have to check. So it is given that ammonia is diffusing through stagnant mixture. So obviously it is the unique component diffusion. That is, ammonia is diffusing through non-diffusing component mixture of nitrogen and hydrogen. Okay, then total pressure that is given in terms of kilonewton per meter square, converted into atmosphere. So what is the conversion factor? 1 atmosphere that is equal to 1.01325 into 10 power 5 Newton per meter square, or in terms of kilonewton per meter square, it is 101.325. Using that conversion factor, you get total pressure in terms of atmosphere. Then temperature 55 degrees Celsius, convert this into Kelvin. Then what is given? Diffusion path distance, that is diffusion is taking place across the film of thickness 0.5 mm. So here you can just visualize ammonia diffuses through nitrogen and hydrogen mixture. Ammonia is only the diffusing component. So this diffusion takes place in the distance of 0.5 mm. So this is given in mm, you convert it into meter and take that as a Z value. Then volume fraction of nitrogen and hydrogen. So this is only with respect to the mixture of nitrogen and hydrogen excluding ammonia. So what is given? 1/3 nitrogen. Apart, in the three parts of total mixture, one part is nitrogen and the remaining two parts are hydrogen. That means 1/3, 1/3, that is nitrogen, that is a volume fraction of nitrogen, and 2/3, that is a volume fraction of hydrogen. So you have YV dash, YC dash. Mole fraction of component B excluding component A. YC dash is mole fraction of component C excluding component A. Then DAB1 and DAC1 data are given as 1.82 into 10 power minus 5 and DAC is 6.86 into 10 power minus 5. So diffusivity of ammonia in nitrogen, diffusivity of ammonia in hydrogen are given. So all the data are available. But what is given here? Diffusivity data corresponding to 1 atmosphere pressure and 25 degrees Celsius are given. But at what temperature and pressure diffusion takes place? It is 55 degrees Celsius temperature and a pressure of 2.0409 atmosphere. So diffusion takes place at a different temperature pressure, but given data is at a different temperature and pressure. So from the given data, you are supposed to find out diffusivity corresponding to process temperature and pressure. So that is what the data given here. So what is the relation between diffusivity, temperature and pressure? For a gas, the diffusivity decreases with increase in pressure, or we can say diffusivity is inversely proportional to pressure and directly proportional to temperature to the power 1.5. So using this relation, you can able to calculate diffusivity at required temperature and pressure. So here I have given the values using that relation, calculated values of DAB and DAC corresponding to this 55 degrees Celsius temperature and this pressure. Let us move on to the solution. So the formula for calculating molar flux, Pt by Rt, D effective by Z, ln of Pt minus Pa2 by Pt minus Pa1. So Na refers molar flux of component A. Pt is total pressure that is given. R universal gas law constant that you are supposed to know, remember. Then T absolute temperature that is also given. Effective diffusivity. For a multi-component mixture, instead of diffusivity A and B, here we have the condition of diffusivity of A and B, diffusivity of A and C. For the multi-component system, we are supposed to find out effective diffusivity and substitute in the formula. I'll tell you how to find out effective diffusivity. Then Z is the diffusion path distance. Pa1, Pa2 are partial pressure of ammonia at film 1 and 2. That is a given data. So as I mentioned, effective diffusivity, how to calculate, let me explain. So the formula is 1 by YB dash by DAB plus YC dash by DAC. Both YB dash, YC dash that is given. DAB, DAC also given. But in the problem statement, these two data are given at different temperature pressure, and using the relation between diffusivity, pressure, temperature, we can find out required data of DAB and DAC at process temperature and pressure. Okay. So that is what shown here. So you need DAB, but what is given is DAB1. And corresponding to this DAB1, the given data of temperature is T1, given data of pressure is PT1. But our process happens at the temperature T and pressure PT. Okay. So substitute the data and find out required data DAB. Similarly, DAC, diffusivity of A and C. So DAC1 is the given data. And corresponding to this given data, the temperature and pressure are T1 and PT1. And the process takes place at a temperature T and the total pressure PT. So substitute these data and find out the required data DAC. After getting these data, substitute in this formula, find out effective diffusivity. Then substitute all the data in molar flux formula and find out molar flux. So D effective by substituting this formula, it is coming around 2 something into 10 power minus 5 meter square per second. And R value, as I mentioned in the previous problems, it's a 0.08206 meter cube atmosphere per kilomole Kelvin. So if you are taking this value, then pressure, you need to substitute in atmosphere, temperature in terms of Kelvin. So all the data are now available, just substitution, and by substitution, we'll be getting molar flux value. So I hope you have understood. Next, we'll move on to the next problem. A vertical glass tube of diameter 0.3 centimeter is filled with benzene at 30 degrees Celsius to a depth of 2 centimeter from top end. After 24 hours, the liquid level in the tube had fallen to 2.5 centimeter from the top end. Estimate the diffusivity of benzene into air if the air above the liquid surface in the tube is stagnant. The vapor pressure and density of benzene at 30 degrees Celsius are 60 mmHg and 0.8 gram per cc respectively. Okay. So this problem is slightly different from what I have explained in the previous case. So what is given here? There is a vertical glass tube which is filled with benzene liquid, and this is open to atmosphere. So from the top surface of the tube, the liquid level that is measured as 2 centimeter initially, and after some time, after 24 hours of time, the liquid level has fallen down to 2.5 centimeter measured from the top surface. So the measurement refers the height that is measured from the top surface of the tube to the liquid surface. It doesn't mention what is the height of liquid that is present in the vessel. So please understand what is given. Okay. So the level is given as the measurement from top surface of the tube to liquid surface. So initially it was 2 centimeter and it had fallen to 2.5 centimeters. Since it is the volatile component, obviously it will vaporize. So due to vaporization, liquid level will drop down and the height which is measured from the top surface which will increase. Then what is given? Estimate the diffusivity of benzene into air. That is what we need to calculate. If the air above the liquid surface in the tube is stagnant. So here atmosphere air is flowing. So this liquid benzene vaporizes. So in the form of benzene vapor, it diffuses through atmospheric air, and the atmospheric air is stagnant. So we can assume this as unicomponent diffusion. And here the diffusion path distance varies as the diffusion continues. So it is not actually steady state diffusion, but it behaves like a steady state diffusion. So it can be taken as a pseudo steady state diffusion problem. Then vapor pressure and density of benzene at 30 degrees Celsius are given. Okay. So now we'll note down all the data. Let us list out the data. So the problem falls under unicomponent diffusion involving pseudo steady state, total pressure, temperature, then height, initial height, final height, then vapor pressure of benzene, which is given as 60 mmHg, convert that into atmosphere. So the vapor pressure at the liquid surface, which is given as 0.07, which is given as 60 mmHg, and at that, after saturation only, you will be getting the vaporization. The vapors will be released from the surface. So at saturation condition, vapor pressure is equal to partial pressure. So the given vapor pressure data, you can take it as the partial pressure of benzene vapor, which can be taken as PA1. Then density of benzene, 0.8 gram per cc, convert that into kg per meter cube. Then time taken is 24 hours. So convert that in terms of seconds. So 24 multiplied by 3600. Then diffusivity data you have to calculate. So we'll move on to the solution. So write the formula for calculating diffusivity. So Z2 square minus Z1 square by 2, rho A by MA, RT by PT, 1 divided by ln of PT minus PA2 by PT minus PA1 into 1 by T. So Z2 and Z1 are final and initial height of liquid measured from the top surface of the tube. Rho A is the density of component A, Ma is the molecular weight of component A, R is gas law constant, T is absolute temperature, Pt is the total pressure, Pa1, Pa2 are partial pressure of benzene at film 1 and 2, and T is the time of diffusion. Let's check whether all the data are given or any data we need to calculate. Z1 and Z2 are given. So initial height 2 centimeter, final height 2.5. convert in terms of meter and you can substitute here. Then density that is given, molecular weight you are supposed to know, benzene molecular formula C6H6, from there find out molecular weight and substitute here. Then R value, so again here also I am going to take the value 0.08206 meter cube atmosphere per kilomole Kelvin. T temperature in Kelvin is substitute, PT total pressure in atmosphere. Then PA1, PA2 data. So PA1 that can be taken from the vapor pressure data of liquid benzene, and PA2. So the PA2 refers partial pressure of benzene vapor at the top surface of the tube. That means at the atmosphere, it's like the benzene vapor concentration is very minimum in air. So the partial pressure of benzene vapor can be assumed as a negligible one. Then T, time of diffusion, that is given, and we are going to substitute in terms of seconds. So the molecular weight, as I mentioned, from molecular formula you can take it at 78 kg per kilomole. Then R value, and PA2 as I mentioned, it can be taken as assumed as negligible. Then substitute all the data in the formula and you will be getting diffusivity of benzene vapor in air. So I hope you have understood all these problems of gas phase and liquid phase under steady state diffusion and also pseudo steady state diffusion. Thank you all for listening. Thank you.